with Mr. Thomas.
Hello, how are you? Good, glad to hear it. Okay, chapter 8, lesson number 9. This is a review lesson for functions and graphs. Bum bum bum. Just like all the other review lessons, this doesn't include every slide and every example. It's just me going over the key points. It's everything that you need to know in this chapter. If there's anything you're unsure of, anything you want in a little more detail, or you want explained a little better, look back at these individual lessons. Or if you want to see more examples on anything, look back at them. So what was this chapter all about? Well, we started with a recap from everything with functions and graphs from higher. I thought it best to give you that rather than just jump into the advanced higher course. So a quick recap, this is everything really that you needed to know and everything that we learned about in higher. I'm not going to cover this in the review lesson here. If you're wanting me to go over any of this, look back to that first lesson in this chapter. I'm just going to keep this review lesson for the advanced higher work. So, with the advanced higher, we started with sketching rational functions. Who remembers what a rational function is? So Hannah, what is it? Brilliant. It is a function that is of the form p of x over q of x, where both p of x and q of x are polynomials. Let's take one that is really basic, such as y equals 1 over x. If we graph it, we get something that looks like this. You can see here that as x tends towards infinity, or towards negative infinity, well, the graph is getting closer and closer and closer to it. So really, as x tends towards positive or negative infinity, the graph gets closer, but it doesn't quite touch. It's the same with y. As y tends towards positive infinity or negative infinity, again the graph is getting closer and closer and closer and closer to it, but it's not quite touching. Really, a line that this happens to, a line that as it goes towards infinity the graph gets closer and closer and closer to but won't touch, is known as an asymptote. So asymptotes are lines that the graph approaches as either the x or y coordinates head towards positive or negative infinity. You can see here that the graph jumps either side of x equals 0, in other words your y-axis, and it's said to be discontinued there. The graph's going to be going down and down and down, and then suddenly on the y-axis, well, the graph doesn't exist. And then just to the right of that, well, it's suddenly bang here at the top. So it's discontinued. A discontinuous function has a break in the curve such as this. If you can draw it though without taking your pencil off the paper, it's known as a continuous function. So we moved on to looking at graphing our functions, and to graph them we have to follow these steps. We need to find out where it crosses the x-axis when y is 0, when it crosses the y-axis when x is 0. And we also have to look at our asymptotes. There are vertical asymptotes. They occur when the denominator equals 0, but you also have to investigate what happens either side of your asymptote. Is a graph going towards positive infinity or negative infinity? And on the other side it's coming from positive infinity or negative infinity. So you need to investigate that. And we've also got non-vertical asymptotes. They're not called horizontal asymptotes because they're not always horizontal. So they are non-vertical asymptotes. And they occur when x approaches positive or negative infinity. So that needs to be investigated as well. And if you are asked for it, if you're really lucky, you also have to look at your stationary points. Woo! So an example looking at sketching a rational function was one like this. Y equals 1 over x plus 2 bracket x take away 3. First thing you have to do is find out where it crosses the x and y axes. So it crosses the y axis when x is 0, you can easily solve that. And it crosses the x axis when y is 0, you can solve that as well. If you end up getting some sort of hocus pocus such as this, 1 equals 0, well obviously that makes no sense, so you have to say what that means. If you end up getting that, it clearly doesn't make sense, so you would say then that the graph doesn't cut the x-axis. That is what that would mean. You would then look at your asymptotes, starting off with vertical asymptotes. They occur when the denominator equals 0. So set the denominator equals 0 and solve that. That means then that you are going to get two vertical lines. They are your asymptotes. It's the lines that the graph will approach and get closer and closer to as it tends towards positive and negative infinity. So you've got a negative 2 and you've got a 3. You need to find out what happens either side. So pick a value just less than negative 2, such as negative 2.1. If you sub that into your original equation, you end up getting a positive value, which means then the graph is going to approach positive infinity. So it looks something like that. It's going to get closer and closer and closer to the asymptote, but not touch. And on the other side as well, if you pick negative 1.9, find out if it's a positive or negative. Because it's a negative, it means it's coming from negative infinity. So you'd have something like that. Do the same with the 3, pick a value just before, you end up getting a negative, which means it's going down towards negative infinity, and pick a value bigger, so 3.1, you get a positive value, so it's coming from positive infinity. So you'd end up with something like that. So that is your vertical asymptotes. You then need to look at your non-vertical asymptotes. And they are going to be what happens as x tends towards infinity. So with your function, you need to think what's going to happen as x gets bigger and 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 bigger. Well, with that, you'd be dividing the denominator, you'd be dividing numerator by a bigger and bigger and bigger number. And if you divide that by a bigger number, well, take 1 divided by a bigger number, well, it's going to get closer and closer and closer towards 0. So you can say then that as x tends towards positive and negative infinity, y would tend towards 0. All you do for your asymptote is you take that part here, replace the tends towards with an equals, and y equals 0 is a non-vertical asymptote. In other words, the x-axis. Once you've done that, take all the information that you have gathered. You find it where it crosses the y-axis. We've just found it doesn't cross the x-axis. We know our non-vertical asymptote and we know our vertical asymptotes, and then you need to graph it. So draw your x and your y-axis, mark on those points that you just found, and then I always like to start with the asymptotes. So with the vertical asymptotes, we know that just before -2, we're going towards positive infinity. So your graph will look something like that. Just after -2 at -1.9, it's coming from negative infinity, so the graph will look something like that. Either side of 3, well, just before that, you've got a negative infinity, so negative infinity is going down towards negative infinity, and positive infinity is what you have at 3.1, so it's going to be a way up here at positive infinity, so the graph will be coming like that. After that, you just want to piece everything else together. Because this is an asymptote as well, you know the graph is going to approach it as it keeps on going. It's the same on this side as well. The graph is going to approach really your x-axis. It's going to get closer and closer, but it's not going to touch. With this part here, you should be able to work out that it is going to cut the y-axis at this point. There's obviously going to be a stationary point somewhere here. We didn't have to find that, but we know after that, because it ends up going towards negative infinity, you would just join them together. So really that is what you would get as your answer. After sketching rational functions, we then looked at improper rational functions. What's meant by an improper function, James? Brilliant. An improper function is where the degree of the numerator is bigger than or equal to that of the denominator. And if that is the case, you have to rewrite it as the sum of a polynomial and a proper rational function. And to do that, you use algebraic long division. Bum, bum, bum. And that has to be used before you can investigate the non-vertical asymptotes. So very quickly, just looking at an example of that, again, if you're asked to sketch this, you can see it's improper. The degree of the numerator, the power of x, largest power of x is 1, largest power of x there is 1 as well. So the degree of the numerator is equal to that of the denominator. So it's improper. Start off the same way. You're going to find out where it crosses the x and y axis. You're then going to look at your vertical asymptotes. Remember, they occur when the denominator equals 0. Investigate what happens either side, so pick a value just before and just after, go out by 1 decimal place and find out if it's approaching positive or negative infinity, or coming from positive or negative infinity. And then it's the non-vertical asymptotes. This is the only difference between this and the previous lesson. So your non-vertical asymptotes, because it is improper, you have to use your algebraic long division to rework it. Remember, for your algebraic long division, I always think Dracula must suck blood. D for divide, M for multiply, S for subtract, and B for begin again. So you divide first of all, divide the first term, so x divided by x will give you 1. After that you multiply, so do 1 times x, which is x, and then 1 times 2, which is 2. After you got your 2 lines, you draw a line underneath, and then you move on to subtract. So x take away x will give you 0. They will always cancel out. If they don't, you made a mistake. And then 4 take away 2 is 2. That there is your remainder. Just check if the degree here is less than that of what you are dividing by, your divisor. It is, so you can stop. You do not have to begin again. So you can rewrite that as, well, this here is your answer. So that there will just be on its own. So you've got a 1 plus, and then this is your remainder, so it's 2 over this x plus 2. So you've rewritten it as a polynomial and a proper rational function. The reason you're doing that is you can clearly see, well, for your fraction here, the denominator, as x gets bigger and bigger and bigger and bigger, well, you're going to be dividing 2 by a bigger and bigger number, meaning then that that will approach 0. If this approaches 0, well, you're just going to be left with this number 1. Therefore, as x tends towards positive and negative infinity, y would tend towards 1. So y equals 1 is a non-vertical asymptote. After that, you're just doing the exact same thing. You just want to piece that graph together. Write down all the information that you know. I always start with the asymptotes as well. You know it's going towards negative infinity. You know it's coming from positive infinity. It's going through these points here, and then this is an asymptote as well. If you want me to explain that in a little more detail, look back at that lesson. After that, we looked at what happens when stationary points are required. So that is the exact same as lesson 3. However, I threw in one example, which is more like an exam style question, where we also had to find stationary points. This was the question here, but you can see we're starting off the same way. We're still finding it where it crosses the x and the y axis. We're then looking at the asymptotes as well. So find the equation of each asymptote. You can do that. Vertical asymptotes occur when the denominator equals 0. You can get that. Think about what happens either side. For your non-vertical asymptotes, because the degree of the numerator is bigger than that of the denominator, you know it's improper, so you have to use your algebraic long division. Dracula must suck blood. After that, well, we then had to find the coordinates of the stationary points. And for the stationary points, you know they occur when dy by dx equals 0. So, when dy by dx equals 0, you're differentiating this. Because you've got one function in terms of x divided by one function in terms of x, you're going to be using the quotient rule, u dash v to qv dash over v squared. Work that out. Set that then equal to 0 and solve for x. After you've solved for x, well, it's the stationary points you want, so you need to find the y value, so sub the x values into the original equation. Do that and you get the values, but then you need to know, is it going to be a maximum, is it going to be a minimum, what's going to happen? Well, use the nature table to find out, or the second derivative, you could use that as well. Either way, you'll find out you get a maximum turning point at 0, 1 and a minimum turning point at 2, 9. After that, you're just wanting to piece that together once again so you can see that you've got all the information, and then you're just wanting to put it into the graph. Again, if you wanted me to explain this, look back to that lesson. There was also a part E thrown in. Sometimes there's a bit that you need to think about. For this one here, it says state the range of values of the constant k, such that the equation f of x equals k has no real solutions for x. Remember, a lot of the time it's written as y equals f of x. So f of x equals k, that there is really your y value. So in other words, where is there no y value? Well, you can see there's y values down at like -5, -4. The graph is definitely down there. There's a y value when x is 0. That's going to be at 1. But up here at y equals 2, there's no solution. Or y equals 3, there's no graph there. Or y equals 4, all the way up to 9. At 9 there is a solution, but just less than that there's not. And the same with just above 1. So you can say that there's no real solutions when k lies in the interval between 1 and 9. So that would be your y value. And when y equals between 1 and 9, there is no solution there for the graph. After that, we went on to looking at sketching the modulus function. So, the modulus signs, this is something that we have come across it before, and really it's the absolute value or the modulus of a real number, and what's meant by that is it's the non-negative value of whatever that number would be. So if you want the modulus of 2, well, that's just 2. If you want the modulus of a negative number, well, you just take what that number is, but you ignore the negative. If we have the modulus of f of x, that is the modulus function is always going to be non-negative. That means then that the graph will always lie above or on your x-axis. It will not lie below. Any bits that do lie below, boom, you flip them above. Any bits that are already above, they remain unchanged. So for example, here we had to sketch the modulus of f of x. That there is f of x, and all we're doing is we're taking this part that is below our x-axis and we flip it above. So it comes up here. Just pay close attention to the points as well. So obviously this -3, 0, it will just stay there. It's on the x-axis. It's not going to be negative, so that's fine. This point here with -2, if you flip that above, it will go to +2. So you're marking that on as well. So just take any parts that are below and flip them above. Sometimes you will be given an equation and you have to sketch that. You should be able to work out what the graph would look like. I always like to sketch what the original is first of all and then flip that. So if you go x squared take away 4, you could always think about where it crosses the x-axis and the y-axis, or you could use your knowledge of quadratics. Y equals x squared is just going to look something like that, and y equals x squared take away 4 will just be moving down 4 units. So you can work out what it will be. From there, this part that is below our x-axis, all you're wanting to do with that is flip it above. So this point at -4, if you flip that up, well, that's going to go to positive 4 up here. So that there will be your answer. That's the modulus of the x squared take away 4. We then looked at odd and even functions. Yeah! If you are given a function and f of negative x is equal to f of x for all values of x, then the function is said to be an even function. And an even function is always symmetrical about the y-axis. So this line here is a line of symmetry, as you can see. And that's because the f of -1 is the exact same as the f of 1. Or f of -2 is the exact same as f of 2. F of -5 is the same as f of -5. You can see that. You get the same thing, so it's going to be symmetrical about the y-axis. On the other hand, if f of negative x equals negative f of x for all values of x, then the function is said to be an odd function. And if you have an odd function, then that will have half-turn symmetry about your origin, just like this. And that's because the f of -1, just imagine that's there, you get this value here. That's going to be the same as the negative of f of positive 1. And the f of -2, well, that's going to be the same as the negative of f of positive 2. So you'd have half-turn symmetry there. What you will need to do is you'll need to determine whether a function is odd or even or neither, and to do that, what you do is you write an expression for f of negative x and then compare it to f of x. And again, if f of negative x equals f of x, then the function is even. If f of negative x equals the negative of f of x, then the function is odd. If you get neither of these outcomes, then it's going to be neither odd nor even. Also, it's useful to know these trig identities and think of the graphs to work these out. Examples then, such as this one, prove the function f of x equals x cubed, take away 2x is an odd function. Well, again, for any of these functions that you have to determine whether they're odd or even, consider f of negative x. So replace x with negative x, and then you want to somehow try and get back to this original. If you end up with the negative of the original, such as here, that equals the negative of f of x, then it means your function is odd. You won't always be told to prove whether it's odd or even. Sometimes it'll just say investigate and then let us know what you think. So for this one here, f of x equals x cubed sine x. Is it odd? Is it even? Is it neither? Start it the same way, f of negative x. Work that out. Because you get back to f of x, then it means it's going to be an even function. After odd and even functions, we then moved on to look at stationary points using the second derivative. So from higher, we know that the first derivative gives us the rate of change of the function with respect to x. Or in other words, if you're thinking about a graph, it gives you the gradient of a curve at a certain point, or the gradient of a tangent at a certain point. If you end up with the first derivative bigger than 0, then it means the gradient is going to be positive. So the graph will be increasing at that point. If it's less than 0, then it means the gradient is negative, so it will be decreasing. And if it equals 0, then it means it's going to be stationary. So in other words, you could have a maximum turning point or a minimum turning point or a point of inflection. And you can use the nature table to determine which. But as well as the nature table, we can also use the second derivative, and that's what we learned in this lesson. So the second derivative finds out the rate of change of the gradient of f of x. So in other words, is the gradient increasing or is the gradient going to be decreasing? That tells us how the slope is changing at each point on the graph. For these ones here, you can see the gradient is constant, it is not changing, so the second derivative will just be 0. For these ones though, you can see that if you take the gradient at this point, and then take the gradient a bit further along, and then a bit further along again, and then a bit further along, well, you can see that the gradient is increasing. It's the same for this one as well. So even though it's sloping down and has a negative gradient, the gradient is still increasing. The gradient here is going to be bigger than the gradient here. Or if you take the gradient at this point, or the gradient at this point, when you go from left to right, the gradient is increasing. If it's increasing, then it means the second derivative is positive, and you would say that the graph would be concave up there. Again, with this one, if you think about the gradient, well, the gradient here is going to be decreasing. Take the gradient there, or take the gradient there, take the gradient there. The gradient for each of these is going to be decreasing from left to right, and the same with this one. If you're going from left to right, the gradient is negative, the gradient is decreasing, therefore the second derivative is going to be negative. That there is going to be concave down. Summing that up then, if the second derivative is bigger than 0, then the stationary point is going to be a minimum. It's going to be concave up, it's going to be positive, so the gradient is going to be increasing. If it's increasing, then you will have something like that. If it's going to be less than 0, then it means the gradient is decreasing, so you'd have something like that. And your stationary point, if dy by dx equals 0, would have to be at maximum. If, however, d2y by dx squared equals 0, then that means it could either be a maximum or minimum or a point of inflection, and you need to use a nature table to determine which. Little diagram that I like to use for this, so if it's going to be bigger than 0, so if it's bigger than 0, it's going to be positive, and if it's positive, it's like a smiley face. So that turning point will be at minimum. If it's going to be negative, it's going to be your sad face, the gradient will be decreasing, so it's going to be a maximum turning point. And again, if it's 0, could be a maximum, minimum, or a point of inflection. An example with that, determine the coordinates and nature of the stationary points on that graph. So you know for the stationary points, they occur when dy by dx equals 0, so set dy by dx equal to 0 and solve for x. After we've solved for x, well, just get the y value as well, so sub that in, and we've got 2 stationary points. But what we need to do is we need to determine the nature, and to determine the nature, we're going to look at the second derivative. So differentiate dy by dx, here we get 12x take away 6, and then you would sub in the x value of the stationary points. If you sub in negative 1, d2y by dx squared is a negative, that means the graph is going to be concave down. So the gradient is going to be decreasing. If the gradient is decreasing, it's going to be negative, it's sad, that means it's going to be a maximum turning point. When you sub in 2, you end up getting 18, it's a positive, so that's going to be concave up, the gradient will be increasing, and that means then that the turning point is going to be at minimum. So you can use the second derivative to determine if your turning point is going to be a maximum or a minimum. And the last lesson we looked at points of inflection. Just remember from higher we found that a point of inflection maybe looked something like that, and they always occurred when you had a stationary point. However, that's not always the case. With this example here, you can see that the gradient going from left to right is going to be increasing, 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 and then it reaches that inflection point. And at the inflection point, the gradient suddenly changes from increasing to decreasing from left to right. So because the gradient changes from increasing to decreasing, that there is a point of inflection. And at that point, because the rate of change of the gradient is not increasing or decreasing, then the second derivative will be equal to 0. However, just because the second derivative does equal 0, it doesn't indicate a point of inflection. You do have to go on and test the concavity. If a point of inflection occurs at a stationary point, then it's known as a stationary point of inflection, such as this. You can see there's your point of inflection. The gradient is changing from decreasing to suddenly increasing, and therefore, because it's suddenly flat, because that's a stationary point, it's a stationary or horizontal point of inflection, and the first derivative would equal 0. With these ones here, the gradient is changing from decreasing to increasing, so again, that there is a point of inflection, but you can see it's not a stationary point. The gradient is not going to be 0, so the first derivative will not equal 0. It's the same with this one as well. So it's a non-horizontal or non-stationary point of inflection. An example with that was this example here, find any points of inflection. You know that possible points of inflection, the second derivative equals 0. So find that second derivative, set it equal to 0 and solve for x. Because you have found that value of x, well, I'm just going to sub that in to find the value of y to get the y coordinate. So we know then there's a possible point of inflection at 0, 0. Why do we say a possible point of inflection? Well, just because that second derivative is equal to 0, it means it could be a maximum, minimum, or a point of inflection. But you know it has to be tested further. And the way you test it is by testing for the concavity. But first of all, I'm just going to look at, is it a stationary point? So if you take that first derivative and replace x with 0, because the first derivative works out to be 8, you know it's not a stationary point. And if it's not a stationary point, then you know it's not going to be a maximum or a minimum. So we're dismissing them. But is it going to be a point of inflection? We'll test the concavity. So that is when you draw up this nature table here, and you take a value just before and just after what you found for x and sub it into the second derivative. If you sub in negative 0.1, you get a negative, and that means that it is going to be concave down. The gradient will be decreasing from left to right. If you sub in 0, you get 0, just double check that. And if you sub in 0.1, well, you end up with a positive in the second derivative. Because you end up with a positive, it means the gradient is increasing. And if it's increasing, it is going to go concave up. Remember, point of inflection is when the gradient changes from concave down to concave up. So the gradient will change from decreasing to increasing. So because there's a change in concavity between the negative 0.1 and 0.1, it indicates that 0, 0 is going to be a non-horizontal point of inflection. So we know it's a point of inflection because it changed from concave down to concave up. And we know because the first derivative is not equal to 0, it's a non-horizontal point of inflection. That is it for functions and graphs. That is a review lesson. That's just a very quick recap. Again, if there's anything you want in a bit more detail, anything you want more examples with, look back to the individual lessons. Good luck with that. Bye.